to hold in mind what an even function is, just think of your parent function f of x equals x squared. So the question mark is this function right here even or odd or neither? So we start off with trying to show if it's even. So you start with this notation, and you put a question mark right there because you're trying to show whether they're equal or not. We don't know yet until we do it. Well, there's nothing to do on the right-hand side because we already know what f of x is. Here it is, right there. There's f of x. So where you see f of x, you replace it with x to the fourth minus 2x squared plus 1. Okay. Now, how do I find f of the opposite of x? What would I do? Amber? That would be if I had the negative outside, like if it reflected over the x-axis, right? Right, this is our input, right? What's in this parentheses is our input. If I said f of -2, you'd put a -2 in everywhere you saw an x, right? So this just says, find the value of the function when I replace x with the opposite of x. Now remember, every time you replace x with anything that has a negative in front, you've got to put it in parentheses. So this is the opposite of x to the fourth minus 2 times the opposite of x squared plus 1. Okay, so I just replace x with the opposite of x everywhere I see it. So remember, this really just says this, -1 times x. That's all it says. It just says -1 times x. It's just, that's how we create the opposite. So when we raise this to the fourth power, we raise the -1 to the fourth power and the x to the fourth power. So -1 times -1 times -1 times -1 is 1. So we get x to the fourth. Now we're going to square the -1 and we're going to square the x. -1 times -1? 1. Does that equal x to the fourth minus 2x squared plus 1? Are they equal? Yep. So this is an even function. So you don't even have to check if it's odd because you can't be even and odd together. You've got to be one or the other or neither. Any questions on using that notation before we move along? Anything? Okay. So today we're starting, if you look up here, polynomial functions in their graphs. So there's going to be some new ideas mixed together with some old ideas. And we've already looked at polynomial functions. We've looked at a linear function, which the highest power is 1. So we call that a polynomial of degree 1. A linear function is a polynomial with degree 1. And a quadratic function is degree 2 because the highest power you see on it is a square, or 2. So we're going to expand these functions now. And the nice thing about polynomial functions is all of your exponents are non-negative integers. So that's 0, 1, 2, 3, 4, 5, all the friendly numbers. We don't have any negative numbers for your powers. That means you have no denominators to worry about and no fractions. So you don't have to worry about roots like square roots and cubed roots. So polynomial functions are really nice looking functions in the sense that all of your exponents, if you look in the examples in number 2, all of your exponents are the nice integers that we're used to working with. Okay. The other thing that we've learned about polynomial function is that the domain of any polynomial function, what's the domain for a linear function or a quadratic function, cubic function? What's the domain? Yeah, all real numbers. So you don't even have to like think too hard about the domains because any number can go in because you're raising them to a non-negative power, which means you never have to worry about dividing by 0 because you'll never have x in the denominator, and you never have to worry about an even root because you don't have any fractions. So these are really cool. The only thing that looks a little funky about a polynomial function is how we have to write it so that it incorporates every possible degree, right? If I was just saying, what does a linear function look like? You could say this, a times x plus b. In fact, that's how it looks in your calculator when we do regression. It says ax plus b. We're used to seeing mx plus b, but when we start using polynomial notation, often we use the a and the b. When we do quadratic, we start with an ax square, and then we have to use the b for your x term, and then we got to introduce another letter at the beginning of the alphabet. What do you think we would write for using this type of notation for a cubic? Anybody want to help me try cubic? Ax to the third, yeah. Bx squared, cx plus a d. And the only condition you would write on each of these is your first coefficient here, which we call the leading coefficient, couldn't be 0, or else you wouldn't have a linear function or a quadratic function or a cubic. All right, so let's look at this notation for a minute. The first thing I want you to notice is that when you have a polynomial of degree n, your degree is always the highest exponent. And when we place your terms in descending order, your highest powered term goes first. And I said term because in between each one of these right here is either a plus or a minus sign depending on the value of a. That's what creates terms. So polynomial is a bunch of terms. Your exponent has a power that's non-negative. And so if you want to talk about the number multiplying x to the n power, the way we designate that is, notice here we don't use a, b, c, d like we did up above. We're using all a. So you know which a goes with which power. You say, hey, if my power is n, then the little subscript on my a is going to be n. And if this was in descending order, if this was a 5, the next one would be 5 minus 1, which is 4. So a sub 4 would be the coefficient that goes with x sub 4. And it goes, and notice it goes dot, dot, dot. Because we know n could be huge. It could be like 100, right? We're not going to fill in all those possibilities here. What would the very last few things look like? Well, it might be a linear term like x. And so its coefficient would be a sub 1. And then we have a sub 0, which represents a constant term. That's a constant. So this is just a constant. It has no variable term. Someone might say, well, Linda, what if I put this on times x to the 0 power? Would that be okay? Well, what's x to the 0 power again? 1. So a sub 0 times 1 is a sub 0. We don't bother putting the x to the 0 there because we understand it to be 1. The coefficient right here that goes with your highest degree term is called your leading coefficient. So today, one of the things we're going to be looking at is the degree of your polynomial and the sign of your leading coefficient, because it's going to tell us something about the graph. So let's just play a little bit with getting used to this new kind of language here. So here's a polynomial. How can I tell this is a polynomial? If I said on your next quiz, give me an example of a polynomial, why would this fit? There's an x squared. What else? Why is this a polynomial? Well, what wouldn't be a polynomial? What would you have to do to something here to make it not a polynomial? Yeah, and do what? So could I do this? If I took that out, would it still be a polynomial? Yeah, it would still be a polynomial. I would just have a 0 x squared term. I don't have, right? So that's still a polynomial. So that was a good guess. What would make that not a polynomial? What could I do? Yeah? Then it would be if I got rid of all my powers and I just did this, it would be degree 0. It's just a horizontal line through 4, still a polynomial. Look at your definition of a polynomial. So what's true about a polynomial, and then undo that, do the opposite. Raise it to a negative power. So if I had something like this, f of x equals x to the negative 3, that's not a non-negative integer for the power. And what would that look like? 1 over x cubed, right? This is an example of something that's not a polynomial. This is called a rational function. Those are coming up next. Rational. So that's not a polynomial. Okay. So here's a polynomial, x to the third minus x squared minus 2x plus 4. What's the degree of this polynomial? 3. It's the highest power you see is the degree. So I'm going to start with the back table, and Di's already answered there. So Alan, what's the leading term here? X cubed. It's the whole first term here. The leading term, you look for your highest power and you put a little box around it, and there it is, x cubed. How about the leading coefficient, Taylor? Look at your leading term, and what's the leading coefficient? No? Want to try again? Okay, sorry, I didn't hear you. I've got people yapping at me here. Okay. 1. Okay. It's the number multiplying x cubed. What symbol would I give that? A sub what? If I go up here and follow my notation from above, up here, it would be A sub what? Sub 3, because that's my leading power, right? So A sub 3. Okay. And Kira, that leaves you for the constant term. 4. That's the last thing. We're going to save this box right here for later after we talk about something. Okay, let's go over to table 3. We've got 4 people over there. So who would like to start us off with the degree? Ashlyn? 5. Perfect. Yep, we got 5. Leading term? Melanie? X5. Okay, does everybody agree with that? So I put a little box around my first term. There it is. Is that the whole thing? Anything else there? Yeah, 3/2, 3/2. That's all right. We're learning. All right, now if you just look at that leading term, Clay, what's the leading coefficient? 1.5 or 3/2, yep. And that's equal to A sub 5 if we were filling out our little polynomial. And constant term here, James, a little tricky. There is no constant term, so what number fills in that spot? 0. Because we wouldn't hurt it if we did that, right? If I put a plus 0 there, it would stay the same. All right. Okay, the middle table, you get to go around twice each. See how exciting that is? So what's the degree for this polynomial right here, Dean? Second degree. And what's the leading term? Okay, does everybody agree with negative 3x, where you take the whole kit and caboodle, right? The sign that comes with it. In this case, since subtraction precedes it, the subtraction sign becomes the sign of the coefficient, okay? What's the leading coefficient, Govani? A negative 3. And what's your constant term here, Govani? 1. All right, and we've got Amber and Fabian. Ooh, you get the hard one. Why is this different than, it's kind of like, does anybody ever do a Seder? Why is this night different from all other nights? Why is this polynomial different from all these other polynomials above it? What's the big difference? It's not in your standard form. It doesn't have pluses and minuses between it, right? They're not terms. What kind of form is this? What do we call this form? Factored form. So if we're going to pick out the highest power, we got to multiply this out. So we have to use the associative property here. We've got this times this times this. So multiply any two of those first.
I think I got it.
Okay, where did you start first, Fabian?
Degree.
No, where did you start with your multiplying out?
Oh, I multiplied minus x squared minus.
So you did these, you multiplied these two first?
Yes.
Okay, and what did you get?
Minus x minus 2x squared.
Okay, so you multiplied that out, and now you got to multiply this times this, okay? And what you get? What did you do first, Amber?
I factored the two things that were in parentheses first.
Yeah, so it's easier when you have something like this. I'm hoping by now you're very familiar with the result of x plus 2 times x minus 2, because those are conjugates. Remember that word, conjugates? And we drop the middle term. We get no middle term here. So you just square the x, you square the 2, and you get a minus in between. So now you can just use your distributive property and you get the opposite of x to the 4th plus 4x squared. So now you can look at that and you can say, oh, now that it's in polynomial form, I look for my highest power. Okay? So what's the degree here, Amber? And what's the leading term? Yep. And leading coefficient, Fabian? And the constant term? 0. Okay, so here's your first little additional notes, okay? Anytime you see a polynomial in factored form and you want to get the degree of the polynomial as if it were written in polynomial form, you can't just look at the highest exponent here too, right? But if you look at all the exponents combined, the exponent on x plus 2 is 1, and the exponent on x minus 2 is 1. And what can you do to these exponents to get 4? Multiply 2 times 1 gives me 2. When you multiply x times x, what do you do to the exponents when you multiply x times x? You add them. So you're adding 1 and 1, you get 2. And then when you multiply x squared by another x squared, what do you do to the 2's? You add them. So what are you going to do to these? You add them. So if you're looking at a polynomial in factored form, like this is, and you want to get the degree, add all your exponents. You don't even have to multiply it all out. So if I just simply asked you for the degree of this to save yourself time, so you say when it's in factored form, add all your exponents. Okay, so in this case, it looks like this. 2 plus 1 plus 1, which is 4. So what if I gave you this polynomial? I'm just going to put some leading coefficient out here. I don't care what it is. And it looks like this. I'll put the 2 there. Okay. What's the degree? Do you feel like multiplying that monster out? Me either. Oh my God, you'd be here for another 15 minutes. Can you find the degree pretty quickly? Someone said 7. How'd you get 7? No, a is just a constant, right? So remember, if you multiplied all this out, you'd have some leading term, right? And the a would just be right there multiplying that, and it would multiply all the rest of the things, okay? What is it? 6. How did you get 6? 2. And what's this one? Plus 2 plus 1. So if you multiplied this all out, and I could probably do it pretty quickly if I wanted to. I could probably do this and then times x plus 1, and I could, I could do this kind of thing, right? But, I mean, I don't want to show off and, do the whole thing out and everything, but, you'd have to do something like this, and then you'd have to multiply it by that, which is x squared minus 2x plus 1. Then you'd have to do that, and then you'd have to multiply it all by x minus 3, and who cares? Because in the end, you're going to get x to the 6th, and then whatever that number is, you multiply all the way through, okay? But who wants to do that when you can simply add the exponents, right? All right. So could you shut the door for me? Thank you. Okay, so what we want to talk about today, one of the new ideas is this last column here, end behavior. And, think about this, it's really important in the end, right, how you behaved in life, right? as your life goes on in the end, whether you're you're going to make it to those pearly gates if you believe in that, right? So we're going to talk about the end behavior of a polynomial, all right? And the end behavior here is this interesting idea. It's the idea of what happens to your function, the value of your function, your output, as x grows forever and ever in the positive direction towards positive infinity, and as x goes towards negative infinity. Does your graph rise forever and ever, or does it fall forever and ever? So here's a function. It's just a linear function. It could be x minus 3/2. That looks like it kind of goes right in between 1 and 2. So this could be f of x equals x minus 3/2. So it looks like this, right? There it is. So what's happening to my value of my function as x is going towards positive infinity? What's happening? I'm waving, hello, rising, right? I'm growing, right, without bound. What happens as I go towards negative infinity? I'm going down, right? So as x moves towards negative infinity, my graph, the value, my output is going down, 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 down. It's going towards negative infinity. Okay, so if my behavior is bad, I go to that bad place. All right. If my behavior is really good, x increases, where do I go? Up, 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 up into the sky. What's the value approaching of my function? Positive infinity, grows without bound. So your book calls that rises to the right and falls to the left. Okay. Now, all I did here was switch the sign of my slope. My leading coefficient changed. Let's suppose this looks like this. F of x equals x minus 3/2. Now what would this look like? The opposite of x minus 3/2. Is that true? Yep, it's the same exact slope. It's going through this. Oh, nope, it's not 1/2 anymore. What's it look like? 2, 4, maybe 3. All right, sorry, I didn't look that closely. All right, maybe this. Is that right? No. What would it be? Doesn't really matter what it is. 1.5x, so we'd have to find the slope. We don't want to do all that. I thought I just reversed these, but I didn't. I didn't look closely. All right. What's the difference here? This has a positive slope. So for a linear function, that means I don't even know really what that a value is. I don't know that it's a slope of 1. I just know that a right here, whatever that number is that multiplies x, is positive. And whatever the number is here that multiplies x is going to be negative. Okay? So now I have my left arm up and my right arm down. And as I move towards negative infinity, what happens to the value of my function? It increases towards what? Positive infinity. And what happens to my function as I move all the way out to the right towards positive infinity? What's happening? Negative infinity. All right. So let's call these arms. Right arm up, left arm down. So when my slope is positive, my right arm is up, my left arm is down. When my slope is negative, my left arm is up, my right arm is down. All you have to think about, folks, when it comes to end behavior is this very basic function, a linear function. A linear function has an odd degree and is 1. And when your slope is positive, your right arm is always up and your left arm is always down, and vice versa. Now the question is, does this hold for all odd degrees? Well, let's look at the next odd function right below it. Here's a cubic function. Does the same thing hold true? Here's a cubic function. This would have a leading coefficient that's positive. Is the right arm up just like on your and your left arm down? And when I make my leading coefficient negative, is my right arm down and my left arm up? So it works exactly the same way. So all you have to know for your odd degree functions is if your leading coefficient is positive, a sub 3 would be the leading coefficient here. If it's positive, your right arm goes up and your left arm goes down. If your leading coefficient here is negative, your left arm is right here. As you move towards negative infinity, that's your left arm. That's going to go up, and your right arm goes down. It works exactly the same as your linear function. So it doesn't matter if I said n equals 15. All you have to know is whatever happens with your linear function happens with any odd function. So it's not like you have to memorize 1,000 different functions. You just have to think about your very basic first degree function, which is odd. Same is true with even functions. Your quadratic function is your first even degree function. What's the first difference you notice when you look at the two pitches for your linear function versus the two pitches for your even function? What's the first thing you noticed about the direction of the arms, the difference between being even and odd? Taylor, can you help me with that at all? Right, so the arrows are both either rising or falling. So they're always going in the same direction, right? Versus your odd functions, one's rising and one's falling. So that's exactly all you have to remember about the difference between even and odd functions. And in fact, if you looked at this quadratic right here, can you tell me anything about a sub 2, the leading coefficient? After we just did quadratics last Wednesday, what can you tell me about the first term here? Well, the x would be squared, yes. I'm talking about the leading coefficient. So it looks something like this. It's positive, and how do you know it's positive? Opens upward, it's a happy parabola. Remember we said when we have a happy parabola, our leading coefficient's positive. And what about this one? Negative, okay? So happy parabola, both arms are rising, rising, rising. So regardless of whether you move to the left towards negative infinity or to the right towards positive infinity, both arms go up. You're happy. Again, when your parabola has a negative leading coefficient, as you move to the left towards positive infinity and negative infinity, your parabola, both arms are down. And guess what, folks? It works the same for x to the fourth power. Look, both arms are up, both arms are down. So you fill in the same exact. So what's important here? When you look at a polynomial, you have to determine, is the degree even or odd? If the degree is even, you're going to be like, touchdown, yeah. Oh, I'm so sad I didn't get a touchdown. Or you're going to be looking like an odd person walking around like this, right? So you first say, is it even or odd? And then you say, is my leading coefficient negative or positive? And all you have to think about, where is your right arm? If you're an even function and you're positive, your right arm is up. So isn't your left, but you only think about the right here because you know they go in the same thing. And if you're an even function and you're a negative coefficient, your right arm is down. So isn't the other one. Right arm up with y equals x with a positive slope, right arm down. So negative leading coefficients, your right arm is down. Positive, your right arm is up. So I'm going to skip really quickly to, before we even get there, here's number 11, right here. Here's a polynomial function. Degree even or odd on number 11? Well, first of all, what's the degree here for number 11? 4. The degree is 4. So that puts us into the even category, right? So you're either a really happy polynomial or a very sad polynomial. Right. And what's the leading coefficient here? What's the leading coefficient? positive 1. All right, if I spell coefficient right, there we go. We'll get it in there. So, do you have to remember what a 4th degree polynomial looks like? No, just remember x squared with it has both arms up with a leading coefficient that's positive. So if you are going to start to graph this, this is your very first step. And all you do on your graph is you do this. Look, boom. You know, whatever happens in between, it doesn't matter that in the end, you're going up like this. So that's the first thing you do when you try to sketch the graph of a polynomial function. This is called determining the end behavior, what direction the function goes as x grows without bound in both directions. Okay. So let's go back to the very first table that we had in the demo, and let's fill out. I'm going to do the first one for you, and then I'm going to have each table do one. So here's our polynomial. It's degree 3. Arms together or opposite? Arms together or opposite with an odd? Opposite. Okay. Is the coefficient positive or negative? Coefficient, leading coefficient, positive or negative? Positive 1. So all I think about is y equals x. Where's my right arm? It's up. Where's my left arm? It's down. So as x moves to the left, my function goes to negative infinity, and as x moves without bound to the right, I grow without bound to positive infinity. So what I'd like you to do now is I'd like table number 3 to fill in this one. And I'd like tables right here in the middle, 2, and table 4 right here, get together after you do it and do this one, tables 2 and 4, and then table 5, this last one, and have a representative come up and fill it in when you're done. Just do one and then you can see what the, okay. So we are now on the demo number, we did 5. 6 and 7 is a total review of something you've already had. We're just reviewing it because this is going to be helpful when we try to graph a polynomial. Zeros of a function. Zeros of a function is what makes your function equal to 0. So when you're trying to find the zeros of your function, you set your function equal to 0 and you solve for x. So I set my function equal to 0 and I solve for x. What else do we call zeros if you were looking at a graph? X-intercepts, right. So before we got to functions and you were just graphing with y and x, like in an elementary or intro algebra class, you would have called zeros x-intercepts. They're the same idea. Exactly the same. All right, so to find the zeros of this function, this comes way back to section 1.6 in your book. You have to solve this polynomial equation. This is a polynomial equation. So one of the big taboos in math is you don't divide both sides by x. You never divide both sides by x because you'll lose one of your solutions. So you never want to divide by x or x squared, any power of x. So what is your choice here? What else can you do to try to have an equation equal to 0? What might you do to solve this? I want to solve for x. How do I solve this equation? Well, I know 0 works because 0 cubed minus 0 squared minus, I can't use quadratic because it's a cubic. Factor. Wee-hee! Factor. What's on your palm? My greatest common friend. What's the greatest common factor here? X. So when you pull out the x, you get an x squared minus x minus 2 left. So your greatest common factor here is your first step is x. And now you must continue to factor because anytime something's set equal to 0, folks, the only way you can solve it is if what's on your other side of your equation is a multiplication problem. That's the only time it will help you. Can we make this, can we factor this any further? Yeah, okay. Some say no, some say yes. Let's see. What is it, Di? Well, what's the factors then? X minus 2x plus 1 is x squared minus x minus 2. Now our job is simple. We set each factor equal to 0, each one of these, and we solve for x. So we get x equals 0 in the first one, x equals 2 in the second one, and x equals -1 in the third. So we call these values of x, we can call them three different things. We can say 0, 2, and -1 are the zeros, they're real zeros because they're real numbers, of the function. We can say x equals 0, x equals 2, and x equals -1 represent the solutions to this equation. We can also say that 0, 0, 2, 0, and -1, 0 are the x-intercepts. If we know a 0, remember we know a factor because we just go backwards. Our factors are always going to look like this. I have 3 zeros. So what do my factors look like? X minus 0, x minus 2, and x minus a -1. So what happens when my 0 is a negative number? My subtraction becomes a plus. So x minus 0 is x minus 2 is x minus 2, and x minus a -1 is x plus 1. And that's exactly the factorization I got right here. So you can work. If you know a 0, you know a factor. We did that a few classes ago, the factor theorem. So if 2 makes a 0, then it had to look like x take away 2. If -1 makes a 0, the factor must have been x plus 1. So when you put a -1 in there, you create a nice big 0. Okay, so let's take a look at this to verify. How are we going to look at it? Well, let's take a look at our function with our graphing calculator. So I'm going to turn it on. And let's go up and put in this function. What is it? X cubed minus 2x squared minus 2x. All right, and we'll just use Zoom 6, which is our standard window, and see what we get. And hopefully it will go through 1, 0, and ooh, I must have put something in there that's wrong because it doesn't go through 2. Did I put minus 3x there? Oh, I put 2 in front of the x squared, so that's definitely going to change it, right? So let's try it again, Zoom 6. Oh, I go through -1, I go through 0, and I go through 1. So I have 3 x-intercepts. I have 3 zeros. They're all different. I have 3 factors. Okay, that's the relationship, folks. You have 3 different zeros. You have 3 different x-intercepts, and you have 3 different factors. Okay, there's the picture for that graph. Let's go back to number 11. We started graphing number 11, so let's keep going here. We've done step 1. We've determined the end behavior. Let's find the x-intercepts. Here's our function, x to the 4th minus 6x cubed plus 9x squared. So how am I going to factor this? Someone who didn't speak up the first time. I know, Dean, you told us how to factor that, didn't you, the first time, the other one? Oh, all right. So how would we start this?
Take out an x squared.
Yep, your greatest common friend here is an x squared, so pull it out. 0 equals x squared times x squared minus 6x plus 9. Okay, now I have to see if my second factor here can be factored. Can I factor x squared minus 6x plus 9? What do I get? X minus 3. And can I write this more compactly other than x minus 3, x minus 3? X minus 3 squared. Okay, so where are my zeros? I have a 0 at x equals 0, and where's my other 0? When x equals 3. So I go down to my graph, and I put an x-intercept at 0, and I put one at 3. So far, that's all I know about my graph, right? That's it. That's all I need to know right now. Okay, so I know about my end behavior. I know about my x-intercepts. The very last thing we have to determine, look at this picture right here. This graph, you know, it's odd because the arms go in opposite directions. Just let's look at this for 1 second. I'm going to see if I can, there we go, blow it up a little bit for you. Okay. Let's see, where is my magic pen? I hope here's my magic pen, I think. Is that no. What happened to my magic pen? Insert, tools, magic pen, right there. Suppose I looked at the x-intercept right here, and I blew that up. Does that look, well, imagine that we're not getting these little, does that look like a straight line through there, right? What about right here? Again, if it was a, you know, wasn't these little Humpty Dumptys. Does that look like, this isn't a good example because of the way the calculator does, not a good example. Because the calculator does these little like pixel things here. Let's see. Let me make this smaller again so I can just keep it there. I'll go to the example that I have on your, oh, I really made this yucky here. Let's, there we go. Put it over there. Here we go. All right. So where are we? We're right here at number 8. I'll use my magic pen on this one. So this could possibly be the function, the quantity x minus 1 squared, because it's shifted to the right. It's x squared. That might be the equation. I don't really care because that's not what I'm looking at here. This says, let's examine the behavior of each polynomial near the real 0, 1. Here's a 0 because y is 0 at 1, and here's a 0. But our function in each of these cases is doing 2 different things near there. So let's kind of zoom in. Let's find that magic pen again. I don't think it stayed up here. So where was that? Under tools, magic pen. And let's sort of just look right in there, just near the 0, and blow it up. Okay, let's blow that up. So if you were only looking at that picture right there, and I asked you what type of function you think this is, what would you say? Right there. Quadratic. Doesn't it look like a parabola? Notice something. If you're to the left of 1, you're above the x-axis. Your outputs are positive. Notice you get to 1 and you bounce right back up. Right? You're still positive. So when you have a 0 where your function behaves like this, your function is coming down and then it bounces right back up. It looks like it would be a parabola if you just zoomed right in there. That tells you something about the factor right here on x minus 1. If you put a 1 in here, you get a 0. It tells you that the exponent at that 0 right there is a 2 because it looks like a parabola. Now, here's a cubic function. I'm zooming in right there at 1. So if I take my magic pen and I zoom right in there, do I bounce when I get close to that 1? Do I bounce right back down like I did in the first one? I'm negative. Do I come right back down? No, I cross over, don't I? So before the 1, all my outputs are negative, and after the 1, so I actually change my sign on either side of that 1. My function changes sign. Now, it's not a straight line. If it was, my exponent would be a 1 on that 0. It's a cubic. It flattens out right there. So that tells you that your exponent on the 0 is a 3. So we say that 1 is a real 0 with multiplicity 2 in this first picture. And here we say 1 is a 0 with multiplicity 3. So if you looked at this picture and I said, how many zeros does this have? You'd say 1, but it really has two. It's just that they're identical twins. In this one, it has 3 zeros. It's just that they're identical triplets. Okay, you have as many zeros as your multiplicity right here says. I want to turn off my magic pen now. Thank you very much. So the multiplicity of a real zero tells us about the graph's behavior near that x-intercept. And this is the summary. If the multiplicity is even, the graph touches. Sometimes we like the word bounces. The x-axis near that zero. I'll get you in a minute, Clay. If the multiplicity is odd, like x to the first or x cubed or x to the fifth, then it actually crosses your x-axis. And the only difference between a multiplicity of 3 and let's say we had this and it was a multiplicity of 1, it might do something over here and then it would go straight through like that. This has a multiplicity of 1 because when you zoom in on it, it looks just like a straight line. Okay, if it was a multiplicity of 5, what would it look like? It would just look something like this. It would start to flatten out even more. But you won't be getting anything with that high of a multiplicity, at least in this class. All right, so in order to determine your multiplicity, you have to have your polynomial function in factored form. That's the only way you can figure out what the multiplicity is. So let's go back to number 11, and then I'll get your question, Clay. All right, so here we are. We have our zeros. Here they are, x equals 0 and x equals 3. What's the multiplicity of my 0 at 0? What's the multiplicity? 2. So that tells me I'm going to bounce or I'm going to touch it. So since I'm coming from this direction, I'm coming down towards my x equals 0. And all I know is I'm just going to bounce right back up. There I am. That's all I can do so far. Just bounce right back up. And my other 0 was at 3. I had one at 0, 0, and 3, 0. Let's look at the multiplicity at 3. Here's my x equals 3. Here's where I put it in. I get a 0. What's my multiplicity? 2. So it's going to act just like a quadratic. So I know I'm going to, on this side, I'm going to bounce up there. So here's the only question. What happens in here? Well, all we're doing is going for a quick sketch, folks. I don't care about accuracy. All you know is if you're bouncing up like this, you got to come back down towards the 3. So you just make a turn like this and come back down. Okay? That's all we're looking for. You're just going to turn around. I don't care how high you go or how low you go. But you're going to bounce up, and then you're going to come back down and then bounce up again. It looks like a W. Clay? Your question was before? What was your question? Nothing? It's gone? Or you answered it?